Hey guys, so with this, we are going to start our first of many review videos. So this one only covers lessons 1 and 2, so you're going to have to watch the following video for the second half of the um, quiz 1 review. So, why are you beeping? Okay, so the first little section is units, right? And it's primarily going to be units of force, mass, and distance because those are the big ones that we use in mechanics in general. And you're going to have to be able to convert pretty freely between these two systems, right? So this is like the foot-pound seconds one. This is the, I think it's standard international. I don't remember actually, but that's like centimeters, whatever, like the metric system. So regardless of what you actually have to do in the problem, you're going to always have a given value. And it'll be converting from, this is an example, so from 32 square feet to millimeters squared, right? So this is your given, is the 32 square feet. And then the desired units is the millimeters squared. So to get from one to the other, you're going to have conversion factors. So on the exam, it's going to be given to you on like a reference sheet. But if you want to look at the reference sheet before the exam, that's found, you're basically given the inside covers of your textbook. So if you want to look at it ahead, that's what it is. But on the quiz, you're going to be given the conversion on either the board or in the problem. So tricks with these, you're going to want to show every single step. That was a problem that was happening on the board a lot, was a lot of people tried to skip the steps that seemed more obvious. And then they ended up like flipping it, or instead of multiplying by 1,000, they multiplied by 0.001 or whatever. So you always want to write out your individual steps regardless of how small they seem, because you get a lot of partial credit in this class, but you can only do that if you get if you show your work. So the other thing that you really need to remember is, so see here how it's feet squared? That means every conversion factor from now on involving feet needs to be squared. So this one, this whole conversion factor needed to be squared. So the conversion factor itself is that 1 foot is 0.3048 meters. But since we're dealing with feet squared, we had to square the whole thing. So then this became meters squared, which means the next time we had to go to the conversion, it ended up being this was squared too. Does that make sense? Yeah, so just make sure that if you have, it's the same thing if it's cubed, everything gets cubed. That involves not only the original unit, but the unit that you're converting to in that factor. So going forward with meters, you would have to square it as well. So the next big thing was scalar and vectors. So the learning outcome was differentiate between the two. So a scalar is just the magnitude. So it's just how strong the value is, and its answer is just the value in the units. So some examples are volume is just measured in milliliters, or whatever. It's not like milliliters to the east or whatever. Density is the same way. Speed and mass are the ones that we're really going to use in this class a lot. You'll see some energy, and obviously we need time, but speed and mass are the ones that are hugely involved in this class. Vector quantities involve the magnitude from before, but it also requires a direction. And your answer is going to look like the value you get plus the units associated with that value plus the arrow in the direction of that value, or that value is going. And then in this class, you use a lot of displacement. You use pretty much all of them, and all of these are examples of vector quantities. Continuing on, trig transformations. So SOHCAHTOA is like super important to remember, and it's especially important to remember that like sine is associated with the opposite angle, even though it might be the horizontal angle. So like same with cosine is sometimes associated with the vertical angle. So a lot of people get stuck in the mindset that sine is associated with vertical and cosine is associated with horizontal. That's not the case. It's opposite and adjacent. So I think I'm gonna actually make another video about slope triangles, because that seems to be a really, really like tough topic in this group, but I go over it a little bit later. It's just something that you need to practice. So I would recommend as many problems as you can. I would recommend doing them just to get used to it. But essentially, you just follow the ratio, right? So the longer side matches with the longer side, and so on. So slope triangles have the same ratio as the triangle it's on. So I'll show you later again, but essentially if this is the slope of the big triangle right here, and it's got like a little tiny triangle, the ratio to size of the tiny triangle is the same as the ratios for the large one. And then another thing to remember is that if you're calculating for an angle in degrees, but your calculator's in radians, you're gonna get the wrong answer. So just make sure you're double checking whether your calculator is in degrees or radians. And if you don't, this is the buttons for the TI-84. If you don't have a TI-84, you can either Google it or reach out to me and I'll help you through it, but that's something you should definitely know how to do. So the next part is force components. So it involves taking this force and breaking it up into its X component and the Y component. So orthogonal is a really fancy way of just saying 90 degrees. So again, it's breaking this up into its 90-degree components. So the fx is 90 degrees away from fy. And then, again, this is where you need to use trig. So this is the part where like you're either given an angle and you have to solve for it with sine and cosine, or you're given like a little slope triangle here, then you have to solve that way. So again, another thing to remember is if it's easier to do it this way, you should rotate the axes so that it's parallel and perpendicular, right? So that instead of fx and fy, you have an axis going parallel to the force that you have and perpendicular to it. So sometimes that just saves time in solving the problem, but either way works. Oh, poo, I didn't finish this slide. Okay, but this is the part that I really, really wanted to go over. So this is an example of a slope triangle, right? You're given a force that goes vertically and upward, so up and to the left. And then they tell you that the ratio of this triangle right here is 3 to 4. And I don't know if you guys remember this, but this is one of the ones that works out nicely. So it's 3, 4, and then 5 along here. So the steps that you want to use, right, is right off the bat, you need to know that this triangle, the yellow one, is similar to this triangle. And by similar, I mean it's just a scaled version of this small triangle. So then the next step is to identify the corresponding sides. So always locate the right angle first. Usually it's pretty easy to do that. And then you find the longer side of the two, right? So that would be the 4 here, and then this one here, right? So the 4 corresponds to this vertical side, and the 3 here corresponds to the horizontal side. And then obviously the hypotenuse stays with the hypotenuse. So then you use the sides of the given magnitudes to find the ratio between the triangles. So here you're given that the hypotenuse of the yellow triangle is 25 newtons, and you know that the hypotenuse of the small triangle is 5. So it's a scale from the 5 that's here up to 25. So that means every side on the small triangle is going to be multiplied by 5 to get to the sides on the larger triangle. So like I wrote down here, it's a 5 to 1 ratio. So 5 times 5 is 25. We knew that from here. But 4 times 5 is 20, which means the vertical side right here is going to be 20 newtons. And 3 times 5 is 15, which means the horizontal side at the bottom is going to be 15 newtons. Over here, I didn't finish the example, but you need to use SOHCAHTOA for this. So this is the example of how you're given an angle, and you need to figure out from that what these two side components are. And remember that when you do that, you end up using, for example, let's solve for b, right? So the sine of this angle is going to tell you information about the opposite, or the side that's opposite that angle. So here, if we take the sine of 30, we get information about b, right? Because it's opposite. So essentially, we know that sine of 30 is equal to the or the opposite of that angle, over the hypotenuse. So b over 25 equals sine of 30, which means if I want to solve for b, I have to do 25 times the sine of 30. And then same with a, but we're going to use the adjacent side since it's touching the side of that angle. A is going to be 25 times the cosine of 30. So this is something big to know because this seems to be more of an issue than this side, but definitely this is something to know. Okay, and this is very important. I didn't find a meme for this, so I put a picture of a puppy and I love it. Real quick, so concurrent and non-concurrent forces. So concurrent means that forces meet at a point, right? And because they meet at that point, there won't necessarily be rotation because they meet there. Non-concurrent means that, so there's a couple forces that are concurrent here, right? Because you can see that that arrow and this arrow meet here. But this, and this are not concurrent because they don't meet here, right? So these might cause rotation, right? So this is important because if you're trying to find the resultant force at, say here, it's a lot easier because the forces are all concurrent through there. But if you're trying to find the resultant force here, you need to know that you don't take into account any of these because they don't actually touch this point at all. So it's like saying, figure out if I push and pull on this door, right? Pretend this is a door. If I push on it and pull on it, whatever, will it open, right? Well, I don't care if someone's opening the door on the other side of the room, right? So this is equivalent to someone opening up a door, picking up a pen, like irrelevant forces to what I'm talking about. So resultant forces, right? So that's the concept of if I'm pulling something this way, right, but also pulling on it this way, how will those two forces combine and interact, right? So the resultant force is a net force acted on by two or more forces, right? So if you break every single force into its x and y components or its parallel and perpendicular components, you can add all of the x's together and all of the y's together to get what the resultant force is going to be. So you have to remember when you do this, you have to define either upwards as positive or downwards as positive and then right or left. It doesn't matter what you choose, but you have to be consistent all the way through. And then that's one thing that I kind of noticed going in this class is if you see more than one force acting on a body, take the sum of the forces, right? And you just, I mean, not every single time, but a lot of the time. So another thing I wanted to go over is what your answer should look like. So another thing, one thing is sig figs, right? So it's 3 sig figs unless the value starts with 1. And if the value starts with 1, then it's 4. Okay? And you shouldn't round for sig figs until the very end of the problem because then you're going to have a compounding error, right? But formatting wise, what should the answer look like? So you're going to have some number and you shouldn't worry about the sig figs of that number until the end of the problem. Because the more you cut it off at the sig figs, the more error you're going to get at the end. Then you're going to have units. So sometimes the question, especially in like the unit conversion questions, sometimes it'll ask for specific units. Otherwise, you should make sure that you're using the proper units to get your answer between 0.1 and 1,000. So if you end up with, I think one of the example questions ended up with an answer of 1,183, that would not be proper because it needs to be less than 1,000. So it would be 1.183 kilonewtons. And then you need a direction. So remember how we're talking about vectors now. You're going to need some indication of how the force is directed. So you could either write it as an angle with some kind of reference, and then you could write it as east if you're talking about direction, or you could label it up, down, left, right. But a lot of the times, especially when we're talking about resultant forces, you could probably write it like that. Another way to do it is you could leave it as a vector. So if you leave it in that bracketed form or the Cartesian form or whatever, you already have an indication of the direction. And lastly, you need a reference point. So it doesn't matter what the direction is if you don't know where you're starting from for that direction. So So it's not enough to just say this. You have to have like some kind of point here, or label the x-axis, and then east from point A or up from point A or point whatever you're talking about. But you need some kind of indication of where you're starting so that you know where you're going. Finally, problem solving. Okay, so this is a big one. You should always draw the picture. You're going to be given a picture on the problem almost every single time, but you should always draw the picture again and ignore, like, you don't have to draw, like, if you're drawing like a leg, like that leg example in lesson 4, don't actually draw the leg, just draw a line. But like, it's super, super important to help the professor see how you're seeing it, because if you're doing it wrong, but you're doing it right in terms of how you saw it, then you get a lot of points for that. So again, draw whatever you need to on the picture, but draw a new and cleaner picture every time. So I usually draw 2 pictures. I draw one that I like add to as I'm reading the problem, and then I go through again at the end of reading the problem and go and draw it again. So you have to have free body diagrams later on. We'll talk about that pretty soon, actually. So I would get used to drawing the pictures. And then lastly, for the pictures, I would use units because it helps you keep track of what you have. You need to use a straight edge so that A, it's to scale a little bit better, and B, it helps with visualizing angles. You should always have like a mini coordinate system or like a reference frame. So like, even if it's just the normal X, Y one like that, or if it's parallel perpendicular, you should always have the little coordinate system, because that helps people keep track of your work and the picture that you drew, especially when it comes to grading. And then this is a big question that I get a lot. What do I do if I get a problem and I totally blank? So every problem is going to give you a value, right? You can't start from nothing. So figure out what the problem is giving you. It might not be directly given, but figure out what you know from the picture, from the given value itself, from the angles, and then figure out what they are asking you for, right? So especially on quiz 1, they're going to be asking you for usually a resultant force, or so usually it's going to be a resultant force. So you start by looking at what you know and how you can connect it to what they're asking you for. And usually that's with an equation, or by separating it into components and then adding them together. Usually there's a certain like associated procedure with it. And once you do that, you have to see what formulas you have at your disposal to get you from the knowns to the unknowns. So here's some test prep tips, some quick formatting things. Exams are usually 3 to 5 questions. They're 100 points each question, and there's a ton of partial credit given. So how you get that partial credit is by following these steps. So every single time you have a problem, draw a picture so that they know what you're thinking. And then draw, I don't know if you guys remember it, but we did a problem that was talking about river distance. It was like a triangle thing, and it said something about river distance. Every single group I talked to pretty much interpreted that differently. So that's why the picture becomes important, because if you show what side of the triangle you were calling river distance, you get points because that was an ambiguous question. So again, draw the picture with the coordinate system next to it, fully labeled with straight edges. That's a lot of points right there. And then you're going to write out the formulas you're using before you plug things into it. So sometimes, and I've done this too, so sometimes I take a formula and really try to like over twist it to my favor. So like a formula that I probably have no business using for that application, I will shove numbers into it. But you don't really get credit for that unless you are using the right formula. But if you plug in vastly wrong numbers into it, it's hard to interpret what formula you're using. So my advice to you would be to write out the formula before you plug values into it. And as of right now, that's not like a huge thing, other than like the moment formula for like M is D perpendicular times the force. That's not like a huge thing. I think that might be the only one that you have right now. But going forward, you're going to have a few of them. and it'll be important to distinguish which one you're using. And then show every single step of your work, no matter how simple it is. Like, even if it's just simplifying, show the steps to simplify it. Write your answers, box them so they know it's the actual answer, and this is what your answer should look like every single time. Reference point is in parentheses because it might not be relevant. And lastly, this is my contact information, my office hours. Please, dear God, text me if you need a fast response because I do not check my email very often, probably only once a day, but I always have my phone on me, so if it goes off, I'll see it. But yeah, so that is lessons 1 and 2. I'm about to sit down and record the ones for 3 and 4, so yeah, see you there.